Hello, my name is Sichen. Today I'm going to talk about security issues on mobile devices. In the past decade, the use of Wi-Fi has become commonplace on mobile devices to connect the internet. Wi-Fi component is kind of an easier point of entry for the attackers. Last year, security researchers found remote attack flaw in the Broadcom Wi-Fi system on chip. Basically, this all comes down to memory corruption vulnerabilities, specifically a stack buffer overflow. They found that with no user interaction, any attacker within the wireless range could send specially crafted packets to these chips that would allow them to execute any code they wanted. This issue is widespread. It can affect any mobile or tablet device that uses this chip. Today, we will focus on how this attack happens. Before diving into the details, I'd like to introduce what is included in this video. First, I would briefly introduce Wi-Fi chip platform, then analyze TDLS vulnerabilities, finally show how to exploit in detail. To start off, let's investigate the Wi-Fi chip. The processor ARM core has ROM, which holds the firmware's code, and RAM, which is used for data processing. When the chip first powers on, the RAM is loaded at address 0 and the RAM is loaded here. We consult the published datasheet and open source driver, combine the RAM and ROM to a single file, and start analyzing. Before hunting for bugs, let's get familiar with Wi-Fi data frame. Each frame has several data chunks called information elements, IEs, which has the structure as TLV, tag, length, and value. When a tag is BTDLS or TDLS, it means TDLS frame. We found a few vulnerabilities related to some IEs in TDLS frame. So what is TDLS? Turnout Direct Link Setup Connections allow peers on the Wi-Fi network to exchange data between one another without passing it through the access point AP, thus preventing congestion at the AP. TDLS has many use cases and supported by most mobile devices. The TDLS frame is like this. This graph shows the high-level flow of TDLS. There are three kinds of phases: discovery, setup, and tear down. When setting up a connection, the peers perform a three-way handshake. Now that we know the TDLS structure, let's take a closer look at the vulnerabilities. In order to ensure the integrity of messages, the corresponding TDLS frames include Message Integrity Codes, in short MIC. This is where we want to make a trick. So how can we find these calculations in the firmware's code? Here is the high-level logic in the tear-down stage. Aha, this IE called Fast Transition IE. Its length field is not checked whether it exceeds the buffer. What a straightforward overflow! See the green field of attacker-controlled data. We can override at most 25 bytes beyond the range of the buffer without verification. Let's start the exploring by the heap implementation. It is a simple best fit allocator, keeping a list of free chunks. When chunks are allocated, they are chosen from the highest address of the smallest free chunk that is large enough. Heap chunks have the following structure. You can see the green fields are used to distinguish the in-use or free chunk. In-use is 0 and free is next pointer. We can plot the state of the free list like this. After sending out crafted TDLS teardown frame, we check the free list. Indeed, one of the chunks in the free list has an exceptionally large size after the teardown. Now it's time to move to the next stage of exploitation. Monitor the state of the heap. This is a snapshot of the state of the heap when we trigger the overflow during the teardump stage. Upper layer is initial heap state. Bottom layer is heap state after creating a TDS connection. We can see that after setting up the TDS connection, most of the heaps used chunks are consecutive, but also two holes are formed. When traces for the teardump stage, following allocations occur. The highlighted trace line donates the allocation of the 256 bytes buffer for the teardump friend's MIC calculation, which we can overflow. Compare the size of the two holes, OX11C and OX124. This one is just bigger than 256 bytes. Think about the best fit rule, so the best fitting chunk for the 250 byte buffer is this one. Using our 25 bytes overflow, we can be able to overwrite first, the header of the next in-use chunk. Second, a few bytes from the contents of the next in-use chunk. We can corrupt the size field of the in-use chunk. Once the TDLS connection is torn down, it will cause the next free operation to create a free chunk whose tail end overlaps another heap chunk. We could try and point the next free chunk at the memory's address, whose contents we'd like to modify. Now we need to find some data structure relating to TDLS which could act as a good candidate for a controlled allocation. This function sends a turnoed probe request over the TDLS connection. It does not require the existence of a TDLS connection in order to be processed. More interestingly, it triggers an allocation with lifetime, size, and contents all in control. Here we also have some modifications to the kernel to make everything work. Let's choose in-use chunks for the next jump for our overflow, because in-use chunks already have valid values. Otherwise, later calls to malloc and free may fail. There are some events in the Wi-Fi standards that must be handled periodically, in which timers is a good choice. Because all the timers are allocated during the firmware's initialization and are therefore stored at constant addresses. Perfect property. Here's the game plan. First, we create two overlapping free chunks. Then, we use the controlled allocation primitive to point the smaller free chunk at one of the timers in the list above. Next, we create another controlled allocation. This one will be the size of OX3C, for which the timer chunk is the best fitting. Therefore, at this point, we will overwrite the timer's contents. But which function do we point our timer to? Well, we can use the same trick. Overwrite another in-use chunk with our own shellcode. After briefly searching the heap, we find a fairly large one, OX400 bytes, and a constant address, perfect for our exploit. We can now hijack a code chunk to store our shellcode, and then hijack our timer to point it at our stored shellcode. Once the timer expires, our code will be executed on the firmware. At long last, we made it. We've seen that while the firmware implementation on the Wi-Fi system-on-chip still lags behind in terms of security. Specifically, it lacks all basic exploit mitigations, including stack cookies, safe unlinking, and access permission protection. Security on Wi-Fi system-on-chip still needs to be strengthened. Hope you enjoyed it. Thank you.